Welcome back to the next TA session. This is TA session number 6 for the course Principles of Signals and Systems offered by Professor Aditya Jagannatham from IIT Kanpur. My name is Yashvanth. I'm presently a Ph.D. student at the Indian Institute of Science, Bangalore, um, aided by the PMRF, that is the Prime Minister's Research Fellowship. My advisor is Professor Chandramurthy, and I work broadly in signal processing and applications to wireless communication systems. I currently focus on the technology called the intelligent reflecting surfaces for 5G and beyond wireless communications. So, if you have any queries about um, the contents that we cover in the TS sessions, you're more than welcome to feel free to, and please feel free to write to me in this email, Yashvanth L @ IISc.ac.in. And if you would like to know more about me, you can navigate to this web link and know more about me. Okay, so the topics covered for this week will broadly include some examples of Z transform and introduction to Fourier series. So Z transform is something that we did in the last class. We saw that the notion of region of convergence, how to invert the Z transform, and how to basically in particular, we saw how to use the partial fraction expansion of Z transform and invert the Z transform. We saw the notion of how to ensure stability, causality of systems, LSI, LTI systems, and we also studied a bit about transfer function. Right, so that was about last week. This week also we'll be continuing a bit on Z transform, and then we will look at some problems on Fourier series also. Okay, so today's class may be slightly short because I thought next week also we will be doing a lot of things in Fourier series. So today will slightly be a short session. Okay, so part 1 of today's session will be to quickly summarize week 6's lectures. Okay, so in the class, professor had walked through several examples on Z transform, how to compute the Z transform, ROC, and many things like that. Okay, so in particular, I have only covered. I have here summarized some important. The other things that we did not see in the last time. The first is basically computing the inverse Z transform using the method of contour integration. So contour integration is a method which is basically used for analytic functions, or very informally what is called a complex function. So recall that Z transform is a complex function because Z variable is a complex variable, right? So it's R e power j omega is basically Z. That means the Z variable in the Z transform is a complex number. So when you want to invert a Z transform, you essentially have to perform complex integration. Okay, and the complex integration, it's not as straightforward as what we do in real integration. In complex integration, you have to choose something called the notion of what is called a contour. Contour is basically a shape, some kind of a shape that you choose on the complex region, and you want to integrate along that particular path or that particular shape. So that's called contour integration. Okay, but without going into further more details, we'll just look at the definition of inverse Z transform. X of Z is a Z transform, then you can show that the inverse Z transform, which will give back the time domain signal or the discrete time signal, is defined as 1 by 2 pi j closed integral over a closed contour gamma x of z z power n minus 1 dz. Okay, here gamma is basically a closed contour which is measured counterclockwise direction, and this contour should enclose all the poles of the function x of z into z power n minus 1. That is, whichever complex in our function you're integrating, the poles of that function should be enclosed within the contour over which you're integrating. Okay, this is basically the method of the contour integration. And it turns out that the answer for such kind of an integral can be obtained in elegant form by what is called the residue method. That is, this integral can be evaluated as sum over I equal to 1 to p, the residue obtained at when z tends to the pole pi of x of z times z power n minus 1. Okay, that is what it says. It is basically sum of residuals evaluated at each pole of the function. Basically, what it means, you take the function x of z into z power n minus 1 and compute the pole of this function. What do you mean by pole? Basically, this you can represent as a fraction, numerator function by denominator function. You check where and all the denominator goes to 0. Those the values of z for which the denominator goes to 0 will constitute the set of poles for the function x of z into z power n minus 1. Now evaluate, find the residue at each of the pole. Okay, each of the pole of the function, and those sum of those residuals is equal to x of n. Okay. Okay, there is also a simple way to, if you recall from complex analysis, if you have done a course on complex analysis, you can also recall that a residue can be easily found by noting down the coefficient of the uh, term corresponding to a pole in the partial fraction expansion of the function x of z into z power n minus 1. Okay, but this is slightly a complicated method because you need to know some basics of complex analysis. So we will just stop with here as far as this is concerned. We will just know that, okay, there is a method you can borrow, you can use from complex analysis also to find the inverse z transform. Okay, so that was the remaining bit from the z transform. Now we will talk about Fourier series expansion of continuous time signals. Okay, so very good. So what we have seen until now in the course include we started our course with, say, what are signals, what are the different types of signals. Then we looked at what are systems, what are different types of systems, and then focused at a special class of systems called LTI systems, and characterized the input-output relationship of an LTI system by means of what is called a convolution. Okay, so that is based, and we saw about Laplace transform. That is the first transform that we learned in this course. So Laplace transform, what it does is you take the continuous time signal and represent the same signal in a different representation, that is different domain, called the Laplacian domain, right? That then we saw several properties of Laplace transforms, and we saw how to compute the Laplace transform using the properties of Laplace transforms, and also how to compute the inverse Laplace transforms, for example, primarily using partial fraction expansion. And we also characterized the input to output relationship of an LTI system using the transfer function, that is a Laplace transform of the impulse response of an LTI system. And then we analyzed in terms of the transfer function, how can we characterize the stability, the causality, the memorylessness properties of an LTI system. And then what did we do? We moved on to Z transform, where we told that Z transform is the counterpart to the Laplace transform, but for a discrete time signal. Just like how a Laplace transform is used for a continuous time signal, for a discrete time signal, it is a Z transform. So that's what we saw in the last week. We again saw different properties of Z transform, how to compute Z transform, inverse Z transform, how to describe the input-output relationship of a system using Z transform, and the property of a system using Z transform. For example, when will a system be causal? When will a system be stable? All those things we characterize using Z transform. So that is what is our story till now. Now, the third type of a transformation is what is called very important transform, called the Fourier transform, right? So it's called the Fourier transform. A Fourier transform is a very beautiful transform. That's because it has an interpretation of the frequency domain representation of a given time domain signal. Okay, so but it turns out that before going into Fourier transform, we will see something called a Fourier series. Okay, Fourier series is basically, so the only difference is that instead of the word transform, we look at series. So it's called Fourier series, and Fourier was a great scientist, mathematician, come scientist, and he basically gave the notion of this Fourier transforms in Fourier series. Okay, again, Fourier series can be defined for both a continuous time system and a discrete time system, but we will now look at only continuous time signals. No, sorry, not systems, signals. Okay, for a discrete time signal, it is called discrete Fourier series. If someone says just Fourier series, in their mind they think of a continuous time signal for which they are analyzing the Fourier series. Okay, so Fourier series is the representation of the continuous time domain signal in the frequency domain or the spectral domain. Okay, and Fourier series is defined only for periodic signals. Okay, there are now two types of Fourier series representations. One is called the complex exponential representation. Okay, so in this representation, let's say x of t is a time domain, continuous time domain signal we have, which is a periodic signal. So if it's a periodic signal, that means it has to have a period of, let's say, t naught. Then what Fourier complex exponential Fourier series representation says is that you can always represent your given continuous time domain signal x of t as the sum of ck times e power jk omega naught t, where k runs from minus infinity to plus infinity, right? So what it says is, okay, ck is some constant that depends on the index k for which you're running the sum, times e power jk omega naught t. Now, what is omega naught? Omega naught is called the angular frequency. That is, it is given by 2 pi by t naught, where t naught is the time period. T naught is the time period. Okay, so this is called the angle. This is all omega 2 pi by t naught is also called the angular frequency of a signal. Okay, fine. So basically, this is what a complex exponential representation says. That is, you take any continuous time domain periodic signal can be represented as a infinite summation over ck e power jk omega naught t, where omega naught is the angular frequency and ck is evaluated by this integration here. That is 1 by t naught integral minus t naught by 2 to plus t naught by 2 x of t e power minus jk omega naught t dt. Okay, so these ck's are what are called the Fourier coefficients. Okay, so this is called the Fourier series representation. In particular, it's called the complex exponential representation of Fourier series. What is complex exponential? This is a complex exponential, right? Because it's an exponent e power some complex number. See, jk omega naught t. So this is called a complex exponential representation of Fourier series. Okay, so ck is basically given by this integration here. In particular, if I look for k equal to 0, see, not just put k, if I put k equal to 0 here, then this here, sorry, then basically here I'll put k equal to 0 or e power 0 equal to 1. So this integration becomes 1 by t naught integral minus t naught by 2 to plus t naught by 2 x of t dt. And this is nothing but the average of this is exactly the average of the signal x of t over one time period, because I'm only considering integrating or finding the area under the curve x of t over one time period minus t naught by 2 to plus t naught by 2, and I'm dividing by the length of the interval 1 by t naught. That's why it's called the average of the signal x of t over a time period. The property of Fourier coefficient is that if the signal is a real signal, then ck star equals c of minus k. That is, the Fourier coefficients represent what is called the conjugate symmetry. Okay, what is by conjugate symmetry? It just says that you take the conjugation of your Fourier coefficient, that is exactly equal to the negative of k. That is, ck star is same as c of minus k. Okay, using this, what you can show is that the magnitude spectrum will have an even symmetry. See, ck is again a complex number. You see, I'm integrating a complex function, so the output of the integral will also be a complex number. So ck is a complex number. For any complex number, you can find the phase and amplitude, right? If I plot the amplitude of ck as a function of k, then you can show that that exhibits an even symmetry. That is, it is, for example, if what I mean, for example, something like this. It's an even, so it's a mod of ck, and x-axis you have k, right? So this basically is an example of even symmetry. That is, it is symmetric about y-axis. Okay, but if you look at for a phase, phase will exhibit what is called an odd symmetry. That is, C of minus k will be equal to minus angle of ck. Okay, so this is called odd symmetry. This holds for a real signal. So that was the story for complex exponential Fourier representation. The next is what is called a trigonometric representation. Okay, in trigonometric representation, your x of t can be written as a naught by 2 plus infinite summation, I'm sorry, the positive summation from k equal to 1 to infinity ak cos k omega naught t plus bk sin k omega naught t. Okay, now where ak and bk are given by this integral here, ak is equal to 2 by t naught integral over one time period. Okay, so for example, if I this the notation integral and underscore, if I say like this means I'm integrating, for example, let's say from any time over one period, for example t minus t1 to t minus t1 plus t naught, or I can just simply write it as from any t naught to t naught plus t naught, or maybe I can say maybe something else. I can simply say 0 to t naught. That's also fine, right? All the notation says is that you need to consider the range of times across one time period of the signal x of t. Okay, recall that we are talking only for periodic signals. So periodic signals always have some finite time period. Fine. So AK is given by this particular integration here, and BK is given by this particular integration here, and A naught also will have basically its own, basically from AK only you can find, put k equal to 0, whatever the integral value that is given by A naught. Okay, so basically this is a trigonometric representation of the Fourier series of a periodic continuous time domain signal. Now, okay, fine. There are two types of representation. Now, what is the relationship between these two representations? It turns out that there are, if you have the complex exponential Fourier series representation, you can find the trigonometric Fourier representation directly. Or if you have the trigonometric Fourier representation, Fourier series representation, you can also readily write the complex exponential Fourier series representation. So for example, if you have the complex exponential Fourier series representation, what does it mean? It means you basically know this kind of a representation where you know the value of ck. Okay, so if you know the values of ck, you can get a naught, ak, and bk by this formula here. Okay, you can get for this formula, and similarly, and then once you have a naught, ak, and bk, you can plug this in this expression for x of t, or in this expression that will give you the trigonometric Fourier series representation of your signal. Yeah, I see a hand raise. What you can do is you can unmute and talk. I think that is better. No need to raise your hand, otherwise I will not know.
In trigonometric representation, where is the A naught value, sir?
Where is the what?
A naught value.
A naught. So put k equal to 0. For example, so this will not be there. It's just this number.
Okay, sir, thank you.
Yeah, so just put k equal to 0 here. Whatever is the integral, that is a naught.
Okay, sir.
Yeah, we can write it, no problem. So a naught is equal to 2 by t naught integral x of t dt over one time period. Okay, fine. So this is a conversion. So if you have one representation of Fourier series, then how to get the representation of the Fourier series in the other domain? So in the first table, if you have all the complex exponential, use these formulas to find out a naught, ek, and bk, from which you can write on the trigonometric Fourier series representation. Similarly, if you have the trigonometric Fourier series representation, that means you know the value of a naught, ak, and bk. Then use these expressions to find the values of c naught, ck, and c minus k. That will help you in writing down the complex exponential Fourier series representation. Okay, so this is you can always convert from one representation to another representation. Now, in particular, for us as a special case, if you know that the continuous time domain signal is a real signal, then what happens is AK and BK will become real, and the relationship between CK and BK will be given by this particular expression. So remember, this expression we'll use today in one of the problems. So for even signals, what do you mean by even signal? X of minus t is equal to x of t. So for this kind of signals, the property is that your BK, that is, what is BK? BK are nothing but the coefficient of sine k omega naught t. So for example, B1 is a coefficient of sine omega naught t. B2 is a coefficient of sine 2 omega naught t. B3 is the coefficient of sine 3 omega naught t. What I'm saying is that for all omega naught, for all such k, if the signal is even signal, all bk's are going to be 0. Why? Basically, why? The reason is simple. So you see, what I want is that I want this x of minus t to be equal to x of t, right? So what I do, I'll first compute x of minus t, and then I'll equate to x of t. Then whatever is the condition I get out of it, it will be that bk will be equal to 0. Why? Because you see, x of t is given by this expression here. Now find x of minus t. What happens? You will have a cos of minus k omega naught t, and here you have a sine of minus k omega naught t. But cos of minus theta is cos theta. But sine of minus theta is minus sine theta. So if bk's were not 0, then this x of minus t will be equal to ak cos k omega naught t minus bk sin k omega naught t. But that is not equal to x of t, right? Because for x of t, you should have plus bk. But when you have x of minus t, it becomes minus bk, right? So basically, if I don't want that to happen, your bk's should all be equal to 0. Only in that case, it doesn't matter whether x sign is there or not, because sine of minus x, although it is minus sine of x, it is multiplied by 0, so that will not come into picture, right? So that explains why for an even signal, your bk's must be equal to 0. Similarly, for odd signal, your ak's must be equal to 0. What is ak? Ak's are the coefficients of cos k omega naught t in the trigonometric Fourier series representation of your signal. Okay. Now conditions. Now find how is Fourier series defined? Fourier series is basically defined as this summation here, right? It's an infinite summation. You're summing up infinite terms. Then what is the guarantee that this infinite sum will converge to some number, right? And that is what is given by the conditions for existence of Fourier series. When will a Fourier series exist? There are some sufficient conditions. Okay, these are what is called Dirichlet conditions. The first condition says that if the signal x of t is what is called absolutely integrable over a time period t naught. That is, if you integrate mod of x of t dt over a time period, it should be a finite number less than infinity. That means the signal x of t is absolutely integrable. X of t has finite number of maxima or minima in any finite time interval, and x of t has finite number of discontinuities, and these discontinuity values should also be a finite gap. It should not be infinite gaps. Okay. These are, if you know that the signal satisfies these conditions, then you are guaranteed that the Fourier series will exist. These are only sufficient conditions but not necessary. What do I mean by that? If you know that these three conditions satisfy, then you can show that Fourier series will exist. But the converse need not hold. That is, if you know that Fourier series exists, it doesn't mean that these three conditions should necessarily satisfy. That is not the claim. If you know that these three conditions satisfy, then Fourier series will exist. That is the only claim that we are making here. Now next, amplitude and phase spectrum of x of t. Okay, what is x of t? Basically is a continuous time domain periodic signal. Now what is an amplitude spectrum? Is basically nothing but you compute ck, that is a complex exponential Fourier coefficients, and you can, since it's a complex number, you can always write this as mod ck times e power j phi k. Now you plot the magnitude of ck as a function of k. Whatever graph you get, that is called the amplitude spectrum of x of t. Similarly, you take the angle of ck, that is basically phi k, and plot phi k as a function of k. Whatever graph you get here is called the phase spectrum. Okay, and these two are discrete signals. Why? Because k is an integer. You see, k ranges from minus infinity to plus infinity, but it takes Go back to the definition, it takes only integer value, k equal to minus infinity or minus infinity plus 1, like that. It takes only integer values. So basically your amplitude spectrum and the phase spectrum will basically be a discrete signal. So it's also called discrete line spectrum. Okay. Now, very important theorem is what is called the Parseval's theorem. This Parseval's theorems will come even in Fourier transform that we will be studying in the next week. So what Parseval's theorem says is that if you take the power of the continuous time domain signal, which is defined as 1 over 1 by t naught integral x mod x of t square dt integrated over one time period, it equals the sum of the square magnitudes of ck. Right? So if you look at the left hand side, this is the time domain power. The right hand side is nothing but the sum of the magnitude squares of all the Fourier coefficients. And what this theorem says is that they both are identical. They both are equal. Okay. So intuitively, I mean, what is the physical meaning of this statement? So what did I tell when I started Fourier series? Fourier series is basically representing the same time domain signal, but in a different domain called the Fourier domain. Right? For a Fourier series is for a periodic signal. Okay, so for a periodic signal, if I want to represent the same time domain signal in Fourier domain, whatever coefficients I used to represent it, they are called Fourier coefficients, right? And what this Parseval's theorem says is that if you compute the power of the signal either in time domain or you compute it in the Fourier domain, okay, the Fourier domain is also called the frequency domain. Whether you compute in frequency domain or the time domain doesn't matter, both will be equal. Therefore, in a frequency domain, the power is defined as just simply the sum over mod ck square, and where sum is taken from minus infinity to plus infinity. Okay. So in fact, there was we saw one claim, right, that ck conjugate is equal to ck conjugate is equal to c minus k for a real signal. We'll just see how this is called conjugate symmetry. We'll see why this should be true. Okay. So here is a small proof as to why this is true. So note that x of t is a real signal. So ck conjugate, we need to prove should be equal to c of minus k. Fine. Okay. Let us write down the definition of ck. What is ck? Is a kth Fourier coefficient, which is defined as 1 by t naught integral minus t naught by 2 to plus t naught by 2 x of t e power minus j k omega naught t dt. What is omega naught? Omega naught is the angular frequency of the continuous time domain signal. Fine. So now what I will do, I will conjugate on both sides. So I'll have ck conjugate and the whole integral conjugate I will do. Now what happens is that this conjugate will go inside the integration. So then that is nothing but x of t conjugate, the whole x of t conjugate into conjugation of e power minus j k omega naught t, which becomes e power plus j k omega naught t. But x of t conjugate is same as x of t. Why? Because x of t is a real signal. For real signal, it doesn't matter whether you do conjugation or not. The value will not change. So x conjugate of t is same as x of t. So this is nothing but 1 by t naught integral x of t into e power j k omega naught t dt. Now I can write j k omega naught t as minus j into minus k omega naught t, but this is nothing but c of minus k. Why? Write down the x. So if a c of k is given like this, what is c minus k? It's nothing but 1 by t naught integral minus t naught by 2 to plus t naught by 2 x of t power minus j minus k omega naught t. Right? That is exactly what we also got here. You see, this is same as this. Both are same. That's why this is equal to c minus k. What did we see? We took the conjugation here and then we simplified it and got c minus k. So for a real signal, ck conjugate is equal to c minus k. Okay. And as a consequence, what happens is that if you take the amplitude spectrum for a real signal, it will be symmetric. That is mod of ck equal to mod ck conjugate equal to mod c minus k. Whereas the phase spectrum will have an odd symmetry. It won't have an even symmetry. That is, angle of ck conjugate is minus angle of ck. Okay, but ck conjugate, what do we know? We know that ck conjugate is equal to c minus k for real signal. So this also means that angle of C minus K equal to minus angle of CK. That's why phase spectrum exhibits a odd symmetry and magnitude spectrum exhibits an even symmetry. So I'll just write it down here. Are there any doubts? Hello? Are there any doubts?
No, sir.
Okay. Now let's start with the next component today. Okay. That is, we'll now do some problems. Okay. So as I told you, so today was basically what I did is I remember doing a lot of questions on Z transform last class itself. So I will do one more question or maybe one or two more questions. I don't remember. Only one question on Z transform, and then we'll get started on Fourier series. We will try to solve two questions, and then we will again solve Fourier series problems on Fourier series in the next week's lectures. Okay. So today's class will be slightly short than regular class. Okay, let's start with the first question. The first question is basically to compute the inverse Z transform of the signal x of z is equal to 1 by 1 minus 0.8 z inverse plus 0.12 z power minus 2. Okay, this is a given Z transform. But we know that multiple time domain, discrete time domain signals can correspond to the same Z transform. So unless you know the ROCs, you cannot uniquely invert. That's why we are now what this question is asking is we want to find the inverse Z transform for different values of ROC. So for in part A, if the ROC is such that mod Z is greater than 0.6, then find the inverse Z transform x of z for where x of z is given by this. Similarly, in the ROC second case, it's mod z less than 0.2. In the third case, mod z lies between 0.2 and 0.6. Okay. So as usual, what did we do? We have to compute the partial fraction expansion of x of z by z. Now, x of z by z means what? So see here, x of z I just rewrote from here. So it is 1 by 1 minus 0.8 z inverse plus 0.2 z power minus 2. Now what I will do is I will take z power minus 2 common. Right. So if I take z power minus 2 common, what happens? Z power minus 2 if I take common, the first term will get z square, second term will get 0.8 z, third term will get 0.12. That is precisely what I wrote here also. Okay. And now 1 by z power minus 2 becomes z square. So z goes on numerator. And so basically now denominator becomes z square minus 0.8 z plus 0.2. Now this can be factorized as z minus 0.6 into z minus 0.2. Now what should I do? I need to find x of this is all for x of z, but I need to find the partial fraction for x of z by z. So what I will do is I will divide by z on both sides into 1 by z. Then what happens is that if I do that, then z and 1 square will go away. So what will happen is you have x of z by z, you'll have x of z by z equal to z by z minus 0.6 into z minus 0.2. Okay. Now, what are the poles of the signal? Very simple. Equate the denominator equal to 0, which means z equal to 0.6 and z equal to 0.2. These are the two poles. They're simple poles because the degree of each of these terms is equal to 1. They occur only once, so they are simple poles. Therefore, the partial fraction expansion of x of z by z can be written as some constant lambda 1 divided by z minus 0.6 plus another constant lambda 2 divided by z minus 0.2. Now, how do you find lambda 1? Lambda 1 is nothing but you take x of z by z multiplied by z minus 0.6 and evaluate that at z minus 0.6. So, look at the what is x of z by z? Okay, let me write down here. So, what do we know? We know that x of z is nothing but z square by z minus 0.6 into z minus 0.2. Therefore, x of z by z is nothing but z by z minus 0.6 into z minus 0.2. Now, what should I do? I need to compute z minus 0.6 into x of z by z and then put z equal to 0.6. So first I'll multiply x of z by z into z minus 0.6. which is nothing but z by z minus 0.6 into z minus 0.2 into z minus 0.6. So this z minus 0.6, z minus 0.6 will get cancelled. So you get z by z minus 0.2. Now this, now put z equal to 0.6. What do you get? You get zero point 0.6 by zero point 0.6 minus 0.2 is 0.4, which is equal to 6 by 4 or 3 by 2. Okay, that is what I wrote here. 3 by 2 is something but 1.5. Okay. Similarly, if I want to find lambda 2, what do? I take x of z by z multiplied by z minus 0.2 now, and then evaluate the resultant at z equal to 0.2. That is, what do I do basically here? So now if I want to do for lambda 2, I get z by z minus zero point 0.6 into z minus zero point 0.2 into z minus zero point 0.2. So z minus zero point 0.2 and 0.2 will get cancelled. So you get z by z minus zero point 0.6 and then put z equal to 0.2. So what do you get? You get 0.2 by zero point 0.2 minus zero point 0.6, which is equal to 0.2 by minus zero point 0.4, which is equal to minus zero point 0.5. It's basically minus 1 by 2, which is minus zero point 0.5. And that's what I wrote here, minus zero point 0.5. Okay, that means what? You can write x of z by z as lambda 1, which is nothing but 1.5 divided by z minus zero point 0.6 plus lambda 2, which is nothing but 0.5 divided minus zero point 0.5 divided by z minus zero point 0.2. Or now you multiply z on both sides. Then what you get is x of z equal to 1.5 z by z minus zero point 0.6 minus zero point 0.5 z by z minus zero point 0.2. Okay, great. Now we have found the partial fraction expansion. Now we need to invert this with respect to the given ROC. Part A. When ROC is such that mod z is greater than zero point 0.6. Okay, what does this mean? This means that you are considering exterior part of the circle mod z equal to zero point 0.6. Right? That means what are the two poles? Two poles are nothing but z equal to zero point 0.6 and zero point 0.2. Let's say z equal to 0.2 circle is this and z equal to zero point 0.6 per circle is this. This is for 0.6 radius, this is for 0.2 radius. And what I'm saying is that the ROC lies outside. That is, this is my ROC. That's what I'm saying now. And what is the inverse Z transform? So you see, if mod Z, if mod Z is greater than 0.6, definitely mod Z is greater than 0.2 also. Right? So for example, if the mod Z equal to 0.8, it's greater than 0.6. Obviously, it's greater than 0.2 also. So for both the terms, Z 1.5 Z by Z minus zero point 0.6 and minus zero point 0.5 Z by Z minus zero point 0.2. For both the terms, the ROCs are exterior part of their corresponding exterior part of the circles with radius equal to their corresponding poles. Okay, therefore it is completely a right-sided signal. Right, you recall a right-sided signal in the time domain will map to an ROC which is an exterior part of some circle. Correct. So basically, go back to the properties. You can find that this will have an inverse Z transform 1.5 times zero point 0.6 power n u of n, which is a right-sided signal. Similarly, the second part will have the inverse Z transform for an exterior ROX for an ROC equal to exterior part of the unit circle as minus zero point 0.5, not unit circle, but circle with radius 0.2, as the inverse Z transform is minus zero point 0.5 times zero point 0.2 power n into u of n, where u of n is a unit step function. Now, let's say you are talking about part B. Okay, no, now my interested ROC is mod Z less than 0.2. That means it's the interior part of the circle Z equal to 0.2. Now, again, if Z is less than 0.2, obviously mod Z is less than 0.6 also. Therefore, here now you are considering the first part is also the corresponds to ROC interior part of Z equal to 0.6. The second part also corresponds to Z interior part of Z equal to 0.2. That means it's both are interior parts. Therefore, your x of n will be left-sided signal. Okay. Therefore, the inverse Z transform will now be minus 0.5 0.6 power n u of minus n minus 1 plus 0.5 times 0.2 power 0.2 power n of u of minus 1 minus n. Okay. Now, finally, if ROC lies between 0.2 and 0.6, that is an annular region, right? So basically what I'm saying is that Z equal to 0.2 is like this, mod Z equal to 0.2 is like this, and mod Z equal to 0.6 is like somewhere here. And what I'm essentially this ROC corresponds to is this annular region between Z equal to 0.2 and 0.6. Now, as far as as far as this z equal to 0.2 is concerned, the ROC is exterior part of the circle. But as far as z equal to 0.6 is concerned, the ROC is interior towards z mod z equal to 0.6. Right? Therefore, you have both interior and exterior coming in the same problem. So that means for the first signal, the ROC is interior of the circle, and for the second signal, the ROC is exterior to the circle. And since an interior part will correspond to a left-sided signal, and the exterior part will correspond to a right-sided signal, addition of an left-sided and right-sided signal will give rise to a two-sided signal. That is, it takes a non-zero value all the way from n equal to minus infinity to plus infinity. Okay, therefore x of n is two-sided. So basically x1 of n is the inverse that transform of the 1.5 times xz by z minus 0.6, but its ROC is interior part of 0.6. Therefore its inverse that transform is minus 1.5 times 0.6 power n into u of minus n minus 1. Similarly, if you take the second signal, that will correspond to an exterior part of the circle with radius equal to 0.2, whose z inverse z transform is given by minus 0.5 times 0.2 n power n into u of n. Therefore, add both of them, you get this particular expression. Okay, so you see the first term is, you see that the first term is a left-sided signal, second term is a right-sided signal, because u of n takes positive values only for positive x n axis, and u of minus n minus 1 takes values only for negative n axis. Okay, are there any doubts till now?
No, sir.
Okay. Now we will start this next question on determining the complex exponential Fourier series representation. Okay, the first question is, I'm given these. So you see, I'm giving a set of five signals. I'm asking what is the Fourier series for each of these signals. How to find the Fourier series? That's the question that I'm asking now. So just give me a minute. I mean, give me 2 seconds. I'll come back. Okay. So first question is what x of t is equal to cos omega naught t. So what is cos omega naught t periodic or not periodic?
Periodic.
Yes, that's why we can write the Fourier series for a periodic signal. Remember, for Fourier series we talk about for a periodic signal. Okay, now let us understand. So basically what I'm asked to do, I'm asked to find the complex exponential Fourier series representation. That is, you need to express the x of t as this infinite summation k equal to minus infinity to plus infinity ck e power j k omega naught t. What is omega naught? Omega naught is equal to 2 pi by t naught, where t naught is the time period of your periodic signal. Now you see, now basically you can write this x of t is equal to cos omega naught t as by Euler's formula. You can write this as e power j omega naught t plus e power minus j omega naught t by 2. Correct. It's a simple Euler's formula for cos omega naught t. Okay. Now what I will do, you take the first series here. That is the actual definition of complex exponential Fourier series, and take the second equation here, which is a decomposition of cos omega naught t in terms of its complex exponential terms. Now what I will do is, what is the frequency? Omega naught is the frequency of the signal, so omega naught is intact. Okay. What I will do is, now you see this first equation here. Just a minute. Yeah. So you see the first equation, right? What does it say? Let me write down here for you. So the first equation here, I can write it a little compactly as it is an infinite summation. So it will have so many, and then it will have, and then let's say c minus 2 e power minus j 2 omega naught t plus c minus 1 e power minus j omega naught t plus c 0 into 1, because e power 0 is 1, and then second term will be C1 into e power j omega naught t plus C2 into e power j2 omega naught t, and then it goes on, right? So it has in minus infinity to it keeps on coming, then something positive, then it keeps on going. It's a minus, this runs from minus infinity to plus infinity. Now you compare your equation in 2 and this infinite summation. How do you compare? You compare the coefficients of the complex exponential terms, right? So basically, you in the cos omega naught t, you only have two terms. You have e power j omega naught t and e power minus j omega naught t, and the corresponding coefficients are half and half, right? So now just do a term by term comparison. What it means that your c minus 1 is equal to half, because it is a coefficient of e power minus j omega naught t, which is also coming in your expression for cos omega naught t. Similarly, your C1 is also equal to half, because that is a uh, coefficient of e power j omega naught t, which is coming in our expansion for cos omega naught t. Right. Therefore, your C1 and C minus 1 are equal to half each. Now tell me, what are the values of C0, C minus 2, C2, C3, C4, and so on? What should be their values? Yes. Correct. Someone answered 0. Exactly. Why? The reason being, see, e power j2 omega naught t doesn't come here. Only e power j omega naught t and e power minus j omega naught t comes. You don't have e power j2 omega naught, you don't have e power 3 j3 omega naught, or you don't have e power minus 3j omega naught. You don't have those terms. Only if you had those terms, you will have some non-zero values for C2, C3, C minus 3, and so on, right? You have only terms corresponding to C1 and C minus 1, and they are equal to half. Therefore, what do we get is that C1 is equal to half and C minus 1 is equal to half, and for any other k for which mod k not equal to 1, that is k not equal to 1 or minus 1, your ck will be equal to 0. I just expanded that here. Okay. So basically, this Euler's formula itself is the complex exponential Fourier series representation of cos omega naught. Okay, so the Euler's formula is the complex exponential Fourier series of cos omega naught. Okay, and it just says that the Fourier series will contain only two terms. One is the C1 corresponding to half, another is C minus 1 that also has a value half. Okay. Now, second signal is what? Sine omega naught t. Same story. Okay, you do the Euler's for by Euler's expansion. Sine omega naught t is nothing but e power j omega naught t minus e power minus j omega naught t divided by 2j. They do the same thing, right? So let's say this, basically here is the complex Fourier series expansion, right? So basically remove this this you remove. Look at just this RHS. This is the complex exponential general formula for Fourier series representation. Okay, what I have is e power j omega naught t, and I have e power minus j omega naught t. That is C1 and C minus 1. The only these two will be non-zero. Everywhere else it will be 0. And what is the value of C1? Tell me. What is the value of C1? Yes, you can unmute and talk. No problem. Yeah. Someone is answering the chat. It is 1 by 2j, because e power j omega naught t has the coefficient 1 by 2j in the Euler's expansion, and the e power j omega naught t comes in Fourier series expansion also. If you compare term by term, C1 should be equal to 1 by 2j. Similarly, tell me what is the value of C minus 1? Yes. Can you please unmute and tell? You're saying same. Is it correct? Is C minus 1 the same as C1? Yeah, with minus, correct. You need, because you have a minus here. So C1 is equal to 1 by 2j and C minus 1 is equal to minus 1 by 2j. Okay, that's what I've written here. C1 is equal to 1 by 2j and C minus 1 is equal to minus 1 by 2j. And similarly but for every other k such that mod k not equal to 1, your Ck will be equal to 0. So again, for sine omega naught t, the Euler's representation itself is the complex exponential Fourier series expansion. Is it clear? Is it clear for everyone? So some of you used to unmute and tell no if it's clear. Is it clear for all of you?
Yes, sir.
Yes, sir.
Okay, sure. Now let's move to the next question. See, part C is x of t equal to cos 2t plus pi by 4. Okay, this is again a periodic signal, right? Because it's just cos 2t. Only thing is now what is the frequency of the signal? It is no longer basically omega naught. Omega naught was some frequency here, but what is the frequency here? Right, we need to first to find the frequency. Why? Because the omega naught in your complex series expansion, your Fourier series expansion is equal to 2 pi by t naught, where t naught is a time period. Okay, first unit. So that your Fourier series representation is basically characterized by two things. One is omega naught value and another value is Ck values. If you know Ck for all k and omega naught, then you know the Fourier series representation of your x of t. So all we need to do is for the x of t equal to cos 2t plus pi by 4, we need to find what are the value of Ck and omega naught. Fine, let's do that. So basically, recall that if I write cos 2t plus pi by 4, what does it mean? The general formula for any cos sinusoidal signal is what? General formula was cos omega naught t plus some phase phi. And what the given signal is what? Cos 2t plus pi by 4. You just compare the term by term. You can show that omega naught is equal to 2 and phi is equal to pi by 4. Therefore, we got the frequency of the signal, that is omega naught is equal to 2. That means your complex Fourier series expansion is of the form x of t equal to, in summation, k equal to minus infinity to plus infinity Ck into e power j 2kt. That is, so we had e power j omega k omega naught t, right? See the expansion for Fourier series. This is expansion for Fourier series. Now put omega naught equal to 2. That's the only thing I did. That's the first thing I did. Okay, put omega naught equal to 2. That is equation 1. Now the only thing that is left out to find is what is the value of Ck. Okay, let's do that. So now x of t is nothing but cos 2t plus pi by 4. Do again Euler's expansion. By Euler's expansion, cos 2t plus pi by 4 is nothing but e power j 2t plus pi by 4 plus e power minus j 2t plus pi by 4 by 2. Now just do some expansion. So this is nothing but half of e power j 2t times e power j pi by 4 plus half of e power minus j 2t minus j pi by 4. But e power j pi by 4 is what? Again by this Euler's the e power j pi by 4 is nothing but cos pi by 4 plus j sine pi by 4. But what is cos pi by 4? 1 by root 2. That is pi by 4 is 45 degrees. Plus similarly j sine 45 is also 1 by root 2. That's where I wrote 1 by root 2 plus j 1 by root 2. And e power j 2t remains constant, same as it is e power j 2t plus half into e power minus j pi by 4 into e power minus j 2t. So if it is e power minus j pi by 4, what happens is that this plus j will become minus j. So here you will get 1 by root 2 minus j 1 by root 2. So that's why there's a minus here times e power minus j 2t. Okay, now tell me, compare this equation 2 and compare equation 1. Can anyone tell me what values of Ck's are non-zero and what are their values? Yes. Yes, tell me. You see, equation 1. Compare equation 1 and compare equation 2. Tell me what values of CKs are 0 and what values of CKs are non-zero. And for non-zero values, what are the values of CK? So basically, just like similar to previous, what did I do? I just compared the coefficients of e power. So in sine omega naught t for the previous question, I just compared the coefficients of e power j omega naught t and e power minus j omega naught t, and told that see e power j omega naught t comes here and e power minus j omega naught t comes here, and I told that c1 the coefficients of e power j omega naught t should be same. Therefore, c1 is equal to 1 by 2j and c minus 1 is equal to minus 1 by 2j. Similarly, that's how I did for the previous question. Now come back to this question. This is for a different signal. Now just look at equation 1 and 2 and tell me what values of CKs are 0 and what are not 0. Correct. Someone already told. Yes. You see, put k equal to 1. If you put k equal to 1, what will you get? You get e power j2t. And that is appearing in the expansion of Euler's expansion. Therefore, C1 is non-zero. And what is its value? It's equal to half into 1 by root 2 plus j1 by root 2. Right? Now, similarly, what you have e power minus j2t. Therefore, you put k equal to minus 1. You will get that term, e power minus j2t also you will get. Therefore, c minus 1 is given by half into 1 by root 2 minus j1 by root 2. Now, what about c other values c2, c3, c4, c minus 2, minus 3, minus 4, c0? What are those values? Yes, 0. Correct. You're right. They are 0. So that's what I'm writing here. You comparing the coefficients between 1 and 2. What I have is that C1 is equal to half of 1 by root 2 plus J1 by root 2, and C minus 1 is half of 1 by root 2 minus J1 by root 2, and CK equal to 0 whenever mod K is not equal to 1. That is when K is not equal to 1 or minus 1. Okay. The next question is x of t is equal to cos 4t plus cos 6t. Okay. See, first of all, tell me, is this a periodic signal? Sum of two periodic signal. Is it a periodic signal? Okay, you're answering the chat. Correct? It's yes. So you can try to. This is a homework. In fact, I think we have done in the first class itself about questions on this. But you can try to show this. Prove that sum of two periodic is periodic. Okay. So this is a property. Therefore, x cos 4t is also periodic, cos 6t is also periodic. Therefore, sum is also periodic, and therefore I can define the Fourier series representation of this x of t. But what is the periodicity of this x of t? That we need to find. Why? Because with omega naught, right? If you look at the Fourier series definition, omega naught is equal to 2 pi by t naught. Therefore, in order to first write the expansion for the Fourier series, you need to find omega naught, for which you need t naught. Therefore, the first step is to find out the periodicity. Or that is the periodic. What is the periodicity of your x of t? That is the first step. What do we do? Go back to the first class. How did we do? Same thing. We found the period for both of the signals separately, and then we took the LCM of the periods of these two signals. That's what we're going to do now. So you look at the first signal, it's cos 4t. Therefore, you can show that the period of cos 4t is given by 2 pi by 4. That is, the trick is you take 2 pi by x, where x is the coefficient of t in the cos 4t. Okay, so you take 2 pi. So the period of cos 4, so for example, in general, period of cos xt is equal to 2 pi by x, right? Or it is not just for cos, it is also for sine. Period of sine xt or sine x cos t, or cos xt is equal to 2 pi by x, where x is the coefficient of t in sin xt or cos xt. So here the coefficient of t is what? 4. Therefore the period, this is a short trick, therefore the period of a cos 4t is equal to 2 pi by 4, which is equal to pi by 2. So every pi by 2 seconds, this cos 4t will repeat. That is the meaning. Similar, you can verify. I mean, it's not so difficult to verify that this is correct. If, for example, if you put what does it mean to say that t1 equal to pi by 2 is a period? That means if you add cos 4t plus capital T, you should get back cos 4t. Okay, now I'm asking for what values of capital T will this happen? Right. So basically, this is nothing but cos 4 small t plus plus 4 capital T, and that means this 4t should be 4 capital T should be an integer multiple of 2 pi. Or if you solve for this, t is equal to n 2 pi by 4. But fundamental period is occurs at for all n integers. Fundamental period is when n equal to 1. Therefore, fundamental period becomes 2 pi by 4, which is same as pi by 2, which is what we showed above also. So the trick, it's a very short trick that you can often use. If you have sine or cos function, then the coefficient of t, whatever be, that coefficient divide by 2 pi, whatever is answer, that will be the frequency. Now I'll just ask you a simple example to test whether this is clearer. Suppose I have cos 100 pi square t. Can anyone tell me what is the period of this signal? Just use this trick and tell me. You can unmute and talk. It'll be slightly faster.
1 by 50 pi.
Correct. So basically what you did nothing but 2 pi by 100 pi square is what you did, which is equal to 1 by 50 pi. Good. So it's a short trick. You don't need to do all these things. You can directly just compute the values using this short trick. Okay. Similarly, what do we do? We will take the period of the second signal cos 60, which is nothing but 2 pi by 6, because 6 is the coefficient of t. Okay, so we have the first signal has a period of 2 pi by 4. The second signal has a coefficient of 2 pi by 6. So what we need to do is we need to take the LCM of 2 pi by 4 and 2 pi by 6. Okay, what do I do? Since 2 pi by 4 and 2 pi by 6 are basically not good integers, or at least looks at a combination of fractions, I will multiply them by a common number and then finally divide. In this case, I will multiply them by 12. Okay, that is basically I'm taking the LCM of 4 and 6 and I multiply by 12 and divide by 12. That will not change the LCM of the actual original numbers. So this is the LCM of 2 pi by 4 and 2 pi by 6 is same as 1 by 12 into LCM of 2 pi by 4 into 12 and 2 pi by 6 into 12. But here 3 times 3 is equal to 12. So 3 into 2 becomes 6 pi. And 6 into 2 becomes 12. And 2 into 2 pi becomes 4 pi. Now LCM of 6 pi and 4 pi, what you can do? Pi is common, so you can take out. So it becomes 1 by 12 pi into LCM of 6 and 4. But LCM of 6 and 4 is what? LCM of 6 and 4 is 12. Therefore, it is nothing but 1 by 12 pi into 12, which is equal to pi. Therefore, the fundamental period of x of t equal to cos 4t plus cos 6t is equal to pi. Pi seconds is the fundamental period. Or the fundamental frequency, that is the angular frequency, omega naught is equal to what? 2 pi by capital T naught. Or it's also equal to 2 pi f naught, where f naught is the frequency the linear frequency, which is equal to 1 by fundamental period. But we saw that t naught equal to pi here. Therefore, just put here 2 pi by pi is equal to 2. Therefore, omega naught is equal to 2. Is it clear till now? Yes. Is it clear?
Yes,
Okay.
sir.
Yes, I assume. Yeah. Thanks. Therefore, you found the first part is over. That is, you have found omega naught. Therefore, your Fourier series representation is of this form. X of t is equal to sum over k equal to minus infinity to plus infinity ck into e power j 2kt. The only thing is I put omega naught equal to 2 here. That's why it becomes j omega naught kt becomes j 2kt. Now I need to find ck. If I find ck, then yeah, we know the Fourier series representation. Now for that, what I will do, I'll go back to my same Euler's representation. X of t is equal to cos 4t plus cos 6t. Therefore, cos 4t can be written as e power j 4t plus e power minus j 4t divided by 2. Similarly, cos 6t is e power j 6t plus e power minus j 6t by 2. Okay, there are 4 terms, so I will just write it in the increasing order of their exponents. So first I'll write the most negative exponent, that is e power minus j 6t by 2, then e power minus j 4t by 2, e power plus j 4t the whole divided by 2, and e power j 6t by 2. Okay, so these are the 4 terms in your Euler's expansion of cos 4t plus cos 6t. Now compare equation 1 and equation 6. Can anyone tell me how are CKs? It should be fairly easy. Yes. Compare 1 and 2. Tell me the values of CK. Simple, right? Let's start with the leftmost term. E power minus j60 is there, but your expansion has e power j2kt. For what value of k will e power j2kt become e power minus j60? Yes. 3. Correct. Not 3. It's minus 3, right? It's minus 3. If you put k equal to minus 3, what this becomes? It becomes e power minus j6t. And similarly, you have that e power minus j60 here also. Therefore, the coefficient c minus 3 is equal to the coefficient of e power minus j60, which is equal to half, 1 by 2. Therefore, c minus 3 is equal to half. Now tell me, for the second term, what will be the corresponding c value? Which c will be non-zero for the corresponding to second term? Yes?
Minus 2, sir.
Correct. So, and what is the value? What is the value of c minus 2? The coefficient, right? Half. The coefficient of e power minus j40 is half. Therefore, c minus 2 will be equal to half. I mean, did you understand this?
Yes, sir.
Yeah. If you didn't understand, you can ask me. I can explain again. There's no problem, because this is, see, I'll tell you one thing. Maybe I'll finish this and I'll tell you. Okay. Now similarly, tell me for the third term. What is the c for which this third term, for what values of ck will the third term correspond to? C2, right? Because here if you put k equal to 2, you get e power j 4t, which is same as what I have in the expansion of x of t. Therefore, C2 will be equal to non-zero, and that will be equal to half. Why half? Because that is the coefficient of e power j 4t in the expansion of the x of t. Therefore, C2 will be equal to half. Similarly, for the last term, you put k equal to 3. You will get e power j60 here and also in the expansion of Fourier series. Therefore, the corresponding C3 will be also equal to half. Therefore, comparing 1 and 2, what we get? C minus 3, C minus 2, C2, C3 all will be equal to half, and every other C will be equal to 0. Okay, basically, let me tell you, basically what's happening here is that actually what you're supposed to do, this is a short trick. Okay, by Euler's formula, I'm giving a short trick to find the Fourier series. Actually, what you should do is, you should, after finding this equation 1, right, you found omega naught. In order to find ck, you know what you should do? You should systematic, a very correct procedure is, go back to the expression. Where is the expression we did in the first, right? This is what you need to use. You need to use the actual definition of ck. Ck is equal to 1 by t naught integral minus t naught by 2 to plus t naught by 2 x of t e power minus j k omega naught t dt. You need to use this for every value of k. You need to compute this integral and then find ck for all values of k. That is how you should actually do. But here we are doing a short trick again. The reason being that these cos and sine signals are nice signals. they are we already know some for standard formulas like Euler's formula, which will naturally represent this cos and sine in terms of complex exponentials. That's why we are just doing term by term comparison. But if it is not a cos or sine, let's say some arbitrary periodic signal, you cannot use this Euler's representation. You have to go with the definition. That is, you need to compute the integral for ck, what we saw in the first notes summary. We will do that in the next example. Okay. Finally, I think we have one more signal. Yes, last signal for second question is x of t is equal to sine square t. Now you see sine square t, what I can do is that, how do I, first of all, first step is to find omega naught. That is, what is the frequency of sine square t. So what I do, I will write sine square t as 1 minus cos 2t by 2. And you can show that this is a periodic signal with omega naught equal to 2. You can try it out. Simple. See, half is a constant signal. There's nothing periodic about it. So period is also periodic because it is equal in every time instant. But the second signal is cos 2t by 2. So if it is cos of the form xt, we'll have the period 2 pi by x. Therefore, here x is equal to 2. Therefore, 2 by 2 will be equal to pi. That will be equal to t naught is equal to pi. Or omega naught is equal to 2 pi by t naught, which is equal to 2 pi by pi equal to 2. That's what I directly wrote to be omega naught equal to 2. Is it clear? Okay, I think it's clear. Yeah. So therefore, we found now x of t can be written as summation k equal to minus infinity to plus infinity ck e power j 2kt. Now the only thing is we need to find ck. Go by the same trick. What I did is that sine square t can be written as e power jt minus e power minus jt by 2j. I mean, basically all I did is sine square t is same as sine t the whole square, right? And what do we know? We know that sine theta is equal to e power j theta minus e power minus j theta by 2j. Here theta is basically the value of t. That's all. Therefore, e power jt minus e power minus jt by 2j the whole square. Therefore, now complete this. I mean, basically expand the square. First term is a square, that is e power 2jt plus b square e power minus j2t minus 2ab minus 2 into a e power jt into e power minus jt. But e power jt into e power minus jt is equal to 1. Therefore, your x of t is nothing but minus 1 by 4. There's a minus down because 2j square is nothing but minus 4. Therefore, minus 1 by 4 take outside common into e power j2t plus e power minus j2t minus 2. Okay. Again, this I can further. Okay. Let it be basically like this only. Now, see the equation 1. This is the general expression for Fourier series of this particular x of t. The actual Euler's expansion of x of t is given by the below term. Now, do the term by term comparison. I have e power j2t here. I have e power j2kt. Therefore, if I put k equal to 1, I will get e power j2t in the equation 1. Therefore, C1 is what? Minus 1 by 4. Right? That's what I wrote. Okay, C1 is minus 1 by 4. Similarly, if I put C minus 1, that is k equal to minus 1, if I put, I will get e power minus j2t, which is also there here, e power minus j2t. And the corresponding coefficient is minus 1 by 4. Therefore, C minus 1 is also equal to minus 1 by 4. Now, the last term that's remaining is minus 2. Now, for what value of k here will this e power, this exponent will become 1? When k equal to 0. Because when k equal to 0, this e power j2kt will be equal to 1. There's only ck. And that is nothing but C0. C0 is equal to 2 by 4 equal to 1 by 2. So therefore, your Fourier series representation of x of t is given by summation k equal to minus infinity to plus infinity ck into e power j2kt, where c minus 1 is 1 by 4, c0 is half, and c1 is minus 1 by 4. And for every other k not equal to 1 or minus 1 or 0, your ck is equal to 0. Is this clear? Yes, is it clear?
Yes, sir.
Yeah, great. So now we will now look at another problem where it is the sine and cos business will not be there. We'll look at some general periodic signal where this shortcut of using Euler's expansion will not work. We need to go with the actual definition. You need to integrate that CK definition was there now. You need to integrate x of t over one time period. You need to do that now. Okay, this is one such example. So basically, you need to. I'm going to consider this periodic square wave. So this is also called what is called a square wave. Okay, that is, so if you look at this wave, basically you see I'm highlighting here, this is like one period. After you elapse this much, again you start to repeat it, right? So go up and then come down, then go up and then come down. So this is basically a periodic square wave, and the fundamental period is what I'm marking here. That is basically one fundamental period for which the square wave repeats. Okay, and I'm saying that the fundamental period is given to be T naught, capital T naught, and basically, for the first t naught by 2 durations, the amplitude of x of t takes the value of a, and for the next t naught by 2 durations, it takes the value 0. That is how I characterize x of t, and this keeps on repeating for every t naught. That is how my given signal is. The first question is, determine the complex exponential Fourier series of x of t. The second question is, determine the trigonometric Fourier series of x of t. These are two questions, and we'll solve it. So again, as usual, first go back and write down what is a complex exponential Fourier series. It is given by x of t is equal to sum over k equal to minus infinity to plus infinity ck e power j k omega naught t. This is the general definition of a Fourier series expansion. That is complex Fourier exponential Fourier series. And what is omega naught is nothing but 2 pi by t naught. Here t naught is given to be the time period, so omega naught you will just be 2 pi by t naught. You don't have any more simplification. T naught is the given time period. You see, t naught is the given time period. Therefore, now what is the value of Ck? Go back to the definition. This is how we define Ck in the initial, right? Ck is equal to 1 by T naught integral 0 to T naught, because we need to integrate only over one time period. We don't need to integrate all over. So I will consider the time period from 0 to T naught. Integral 0 to T naught x of t into e power minus jk omega naught t dt. Go back. This is the definition of Ck. I'll go back to the first page again. Yes, you see here, x of t is equal to summation over ck e power jk omega naught t, where ck is equal to 1 by t naught integral minus t naught by 2 to plus t naught by 2 x of t e power minus j k omega naught t. Yeah, you can argue that here it is minus t naught by 2 to plus t naught by 2, but I'm using 0 to t naught. It's okay, because I only need to integrate over one time period. It doesn't matter what is the exact starting and ending. Should be within one time period. Either minus t naught by 2 to plus t naught by 2 or 0 t naught, doesn't matter. It should be over one time period. That's all. So for example, if you see the time period here, what is the time period? What is the interval width here? Minus t naught by 2 to plus t naught by 2. That is a t naught. You're integrating over t naught, a width of a time period of t naught. Same thing only I am also doing here. There is no difference in that sense. Okay, so ck is equal to 1 by t naught into integral 0 to t naught x of t e power minus jk omega naught t dt. Now you see the value of x. Go back to the given x of t. X of t takes the value a, some non-zero amplitude a, from 0 to t naught, and from t between t naught by 2 to t naught, it takes the value 0. Right. So that it's a split function. The actual x of t is a split function between two values, a and 0, in different time intervals. Therefore, I split this integral into two integrals, one from 0 to t naught by 2, and the other is from t naught by 2 to t naught. Right. Now, from t naught by 2 to t naught, x of t is 0. Therefore, second integral will go to 0. It won't survive. So the only integral that survives is the first integral. And in this case, between 0 to t naught by 2, x of t takes a constant value equal to a. Therefore, ck is also equal to 1 by t naught integral 0 to t naught by 2 a times e power minus jk omega naught t dt. Now a is a constant, so take it out. So it becomes a by t naught into integral 0 to t naught by 2 into e power minus jk omega naught t dt. Now this is like a normal integration, like e power jx with respect to x integral. What do you do? e power jx by j, right? The same thing. So you're integrating with respect to t. So basically the integral of e power minus jk omega naught t will be e power minus jk omega naught t divided by the coefficient of t, which is minus jk omega naught, and limit it from 0 to t naught by 2. So basically we'll do that. So you get a by t naught into, first apply t naught by 2. So you get e power minus jk omega naught by 2 omega naught into t naught by 2 minus e power 0, which is 1, divided by minus jk omega naught. Now just the minus you compensate by swapping the two terms on the numerator. You get a by jk omega naught t naught, because this jk omega naught into t naught becomes jk omega naught t naught into 1 minus e power jk omega naught t naught by 2. But what is omega naught? 2 pi by t naught, right? Therefore omega naught t naught is equal to 2 pi. Therefore you put omega naught t naught equal to 2 pi here. So what do you get? You get ck equal to a by jk 2 pi. See, here also you have omega naught t naught, so that also you put 2 pi. Here also you have omega naught t naught, that also you put equal to 2 pi. So you get a by jk 2 pi into 1 minus e power minus jk pi. That is this, when you have 2 pi, 2 and 2 get cancelled, so you get e power minus jk pi. That's what I wrote here. But e power minus jk pi, I can further simplify it as what? E power minus j pi whole power k. But what is e power minus j pi? Cos pi minus j sin pi. But sin pi is 0, cos pi is minus 1. Therefore, e power minus j pi is minus 1. Therefore, your ck is nothing but a by jk 2 pi into 1 minus minus 1 power k. For example, okay, so this doesn't hold for k equal to 0. Can anyone tell me why this is not valid for k equal to 0? Yes? Can anyone tell why this is not applicable when k is equal to 0? What happens when k is equal to 0? Hello? Am I audible? Hello?
Yes, sir, audio.
Okay, okay. Yeah, I think my internet went off in between. Yeah. Okay. When k equal to 0, what happens? Right. So basically what you get, put k equal to 0 here. So it becomes 1 minus 1. So numerator is 0. Denominator also goes 0. So it is a 0 by 0 form. Therefore, this ck at k equal to 0, this is not the thing you need to do. So what you need to do, I will tell you. So when k is not equal to 0, for whenever k is even, that is, let's say k you can represent as k equal to 2m for m in integers, right? Then what happens is, for those even integers, your minus 1 power k is equal to 1. Then it's 1 minus 1, so ck will be equal to 0. But when k is equal to odd, then you can write your k to be, your minus 1 power k will be equal to minus 1, or 1 minus of minus 1 is equal to 2. Therefore, your ck will become 2 by jk 2 pi into a. 2 and 2 get cancelled, so you'll get a by jk pi. Okay, so these are the values when you have ck, when k is even, when k is odd, for non-zero value of k. Now, when k becomes equal to 0, the ck becomes 0 by 0 form. So what you should do is, you should go back to the definition of ck, which is this integral, right? Now put k equal to 0 right here. Before computing the integral, you put k equal to 0. Then what happens? So c0 becomes the only depends on k in right hand side is e power minus jk omega naught t. Put k equal to 0, then it becomes e power 0, which is equal to 1. Therefore, c0 is equal to 1 by t naught integral 0 to t naught x of t dt. Again, you're basically what it means, you're only computing the area under x of t and divide over one time period and dividing by the time period. So by x of t, but we know that from 0 to t naught by 2 it takes the value a, and from t naught by 2 to t naught it takes the value 0. Therefore you can split this integral into two parts. The second integral go to 0. So first integral is 0 to t naught by 2 into a dt. But a is a constant, take it out, so it becomes a by t naught into t naught by 2, which is equal to a by 2. Therefore you can summarize, right, that C naught, so basically your Fourier series representation basically can be summarized as follows: complex exponential Fourier series. Okay, C naught is equal to a by 2. Your C2m, that is for even values of integers, even valued integers, the C is equal to 0. And similarly for odd valued integers, your C, that odd value will be equal to a by j into 2m plus 1 pi. You see, I'm only saying that k is equal to 2m plus 1. Go back to the expression here. I told for odd k it is a by jk pi, right? Put k equal to 2m plus 1, and that's what I'm writing here. Therefore, your x of t can be written as C naught, which is basically, C naught, which is equal to a by 2 plus a by j pi. It is a constant, take it outside summation, which is the second term here. And summation m equal to minus infinity to plus infinity 1 by 2m plus 1 into e power jk omega naught, right? But k is equal to 2m plus 1 into omega naught t, where omega naught is equal to 2 pi by t naught. Is this clear? This is the answer. Someone asks you what is the complex exponential Fourier series representation of the square wave, this is the answer. Is it clear? Is it okay?
Yes, sir. Yes.
Okay. Now second part is what? We need to find the trigonometric Fourier series representation. Okay, so for that, what we will do is we will make use of the fact that the given x of t is real, because it takes only two values. It takes the value either a or 0. Both are real numbers. A is a real number, 0 is also a real number. Therefore, x of t is a real number for any t. Therefore, you go back to the relationships I told you in the starting of this today's session, the part 1. So for real signal, your a0 is equal to 2 times c0, and you know that c0 is equal to a by 2. Therefore, a0 becomes a. Your a2m equal to b2m will be equal to 0. That is, whenever the even indices come, the corresponding a's will become 0. And what we know is that for all odd indices, your a2m plus 1 is equal to 2 times real part of c2m plus 1. But c2m plus 1 is what? 0, because odd of c2m plus 1 is basically 0. I mean, see, c2m plus 1, what is c? This is c2m plus 1. A by j into 2m plus 1 into pi. It's purely imaginary because j is there. It's not a real number. It's a purely imaginary number. Therefore, real part of the c2m plus 1 is 0. Next is what? b2m plus 1 is given by minus 2 times imaginary part of c2m plus 1. So now what is the imaginary part of this? See, you need to bring j up. J up is generally you need to, so this is same as minus j into a by 2m plus 1 into pi. Therefore, imaginary part of this is nothing but minus a by 2m plus 1 into pi. But there's a minus 2 outside. So minus and minus will cancel and just multiply by 2. So you get 2a by 2m plus 1 into pi. Therefore, you got a values for both even and odd integers and at a0 also. Therefore, substitute. So a0 is the first a by 2. You have a0 by 2 in your expansion for trigonometric. That's why another 2 came. But a0 is actually a. And you only take into account the bm and 2m plus 1. That means you see a basically for even integer anyway it is 0. For odd integers also it equals 0. Therefore, there will be no cost term at all. Only sign terms will exist, and that too only for odd sign terms, not for even sign terms. Even sign terms anyways b2m is 0. Only odd coefficients will exist, whose coefficients are given by 2a by 2m plus 1 into pi. Okay, so that is what I wrote here. Okay. So in fact, if you want me to expand what this is how the sine wave looks like. I mean the square wave looks like. Basically, this means I'm saying sine omega naught t plus 1 by 3 sine 3 omega naught t and so on plus 1 by 5 sine 5 omega naught t and so on. This the whole multiplied by 2a by pi plus a by 2. This is the trigonometric Fourier series representation of your given x of t. Is it clear? Hello? Is it clear or shall I explain once more? Yes? Any answer? Is it clear or shall I explain once more? Can anyone reply?
Yes, sir. Clear, sir. Clear.
Okay, it's clear. Okay, great. So now let me clarify one thing. Why intuitively, whether this answer is correct or not, there is one short trick to verify whether this answer can be correct or not. Okay, you see, go back to the actual signal x of t. You see, this has some structure like this, right? And if you take x of minus t, for example, you can show that this is equal to minus x of t. That is, this signal is an odd signal. Because you see, this is exactly anti-symmetrical about your y-axis. See, whenever it was 1, here it is 0. And whenever it was 0, it was 1 in the negative axis. It exactly anti-symmetrical. So x of minus t is equal to minus x of t. This is anti-symmetrical signal. Therefore, for these kind of signals, you basically should not expect cost terms, right? Because if you had cost terms, then that would mean that you are having even part. But this signal is not an even signal. X of minus t is not equal to x of t. That's why you had only sine components in your final trigonometric expansion. The square pulse contains only odd harmonics. Okay. In fact, let me do something better. What I will do is I'll shift the given signal slightly by left by an amount of t naught by 2. Like this. So instead of having something like this, so maybe I'll draw here. Instead of having like this is what we had now, right? I will, okay, sorry. This is what we had now. I will shift this signal slightly towards left like this. And that is what is this x2 of t. Now find the Fourier series expansion, trigonometric Fourier series expansion, and show that this will only contain cos terms and no sine terms. Because the even signal, you see, it's symmetrical about y-axis. It's an even signal. Now it's a homework for you. Maybe we'll do this. We'll start this as a first question in the next class. So what I'm trying to say is that if you compute the trigonometric Fourier series expansion of this modified x2 of t, this will not contain any sine terms. It will only contain cos terms. You can try it as a homework and let me know if you're getting it in the next class. Okay, so I only have this much for today because I thought I will cover more such examples in next class on Fourier series. So if there are any questions, I can take now, or else we can stop for today.
Close for today, sir.
Sorry,
No, sir.
I didn't hear you. You have no doubts, is what you're saying?
Yes, sir. Yes, sir. No doubts.
Okay. How about others? Is everything clear till now? Okay. Since I'm not getting any reply, I assume that it's clear for all of you. So then let's do one thing. Let's stop for today here, and we will continue again in the next class.
Thank you, sir.
Yeah, sure.